Welcome to day 8 of Master AI in 30 days. Over the past week, we've explored AI's technical foundations, mathematics, machine learning, deep learning, NLP, computer vision, and reinforcement learning. Today, we shift focus to equally important topics: ethics, responsibility, and societal impact. AI isn't just technology. It's technology deployed in the real world, affecting real people's lives. AI systems make decisions about loans, jobs, criminal sentencing, medical treatment, and content people see. These decisions have profound consequences. Without careful consideration of ethics, fairness, privacy, and safety, even technically impressive AI can cause harm. Today, you'll understand AI bias and fairness, how algorithms can amplify historical inequalities, and what fairness means in different contexts. You'll learn about privacy-preserving AI, including federated learning and differential privacy. You'll explore explainability and interpretability, understanding what AI systems learn and why they make specific decisions. You'll examine AI safety and alignment, ensuring systems behave as intended. And you'll discuss broader societal implications. By the end of today, you'll understand that building AI responsibly requires more than technical skill. It requires ethical consideration, awareness of societal context, and commitment to fairness and safety. Let's explore how to build AI that benefits humanity while minimizing harms. Here's what we'll accomplish today in AI ethics and responsibility. First, we'll understand AI bias, where it comes from, how it manifests, and its real-world impacts. Bias can enter through training data reflecting historical discrimination, through feature selection emphasizing certain characteristics, through model architecture, or through deployment contexts. Understanding bias sources is the first step toward mitigation. Second, we'll learn fairness metrics. What does fair mean algorithmically? Different definitions exist: demographic parity, equal opportunity, equalized odds, individual fairness. These metrics often conflict. Achieving one type of fairness may preclude another. Understanding these trade-offs helps make informed decisions about fairness priorities. Third, we'll master privacy-preserving AI techniques. Federated learning trains models on distributed data without centralizing sensitive information. Differential privacy adds carefully calibrated noise, enabling statistical analysis while protecting individual privacy. These techniques balance utility and privacy, crucial for deploying AI on sensitive data. Fourth, we'll explore explainability and interpretability. Why did the model make this specific prediction? What features mattered most? Techniques like SHAP, LIME, attention visualization, and saliency maps help interpret model decisions. Explainability builds trust and enables debugging. Fifth, we'll examine AI safety and alignment. How do we ensure AI systems behave as intended? Specification, gaming, reward hacking, and goal misalignment create risks. Safety research addresses robust specification, value alignment, and verification. After today, you'll approach AI development with ethical awareness and responsibility. AI bias isn't a single phenomenon. It arises from multiple sources throughout the ML pipeline. Historical bias occurs when training data reflects societal biases and historical discrimination. If hiring decisions historically favored men over equally qualified women, a model trained on this data learns discriminatory patterns. The model doesn't see bias. It sees correlations and patterns that happen to encode discrimination. Historical bias is insidious because the data is accurate in reflecting past decisions, but those past decisions were biased. Representation bias happens when certain groups are underrepresented in training data. A face recognition system trained mostly on lighter skinned faces performs poorly on darker skinned faces. Medical AI trained mostly on data from one demographic may not generalize to others. Underrepresentation leads to poor performance for minority groups. Measurement bias occurs when we measure outcomes differently for different groups. Recidivism prediction systems might have different error rates for different racial groups because recidivism measurement itself is biased. Some communities face more intensive policing, leading to higher recorded recidivism regardless of actual behavior. Aggregation bias arises when we use one model for populations with different characteristics. A diabetes risk model trained on aggregate data might miss that different ethnic groups have different risk factors. One-size-fits-all models can perform poorly for minorities. Evaluation bias happens when test sets don't represent deployment contexts. A model evaluated on curated, balanced data might fail when deployed on real-world, imbalanced data. Evaluation bias creates false confidence in model fairness. Defining fairness mathematically is surprisingly complex. Multiple incompatible definitions exist. Demographic parity, statistical parity, requires that positive prediction rates are equal across groups. If 10% of group A is predicted positive, 10% of group B should be predicted positive. This ensures equal treatment rates but ignores whether groups have different base rates of the outcome. If groups genuinely differ in outcome prevalence, demographic parity may be inappropriate. Equal opportunity requires equal true positive rates, recall, across groups. Of people who truly deserve positive outcomes, equal percentages should receive them across groups. This is relevant for outcomes like loan approval. We want equally qualified applicants from different groups to have equal approval rates, but it allows unequal false positive rates. Equalized odds requires both equal true positive rates and equal false positive rates across groups. This is stricter than equal opportunity. It ensures that both benefits, true positives, and harms, false positives, are distributed equally. But achieving equalized odds is difficult and may reduce overall accuracy. Individual fairness requires that similar individuals receive similar predictions regardless of sensitive attributes. Two people identical except for race, gender, etc. should receive identical predictions. This seems intuitive, but defining similar is challenging, and it doesn't address systemic advantages one group may have over another. The impossibility theorem shows these definitions often conflict. Except in special cases, you cannot simultaneously achieve demographic parity, equalized odds, and calibration. Achieving one fairness metric may violate another. This forces difficult decisions about which fairness matters most for specific contexts. Mitigating bias requires interventions throughout the ML pipeline. Pre-processing techniques address biased training data before model training. Resampling balances representation across groups, oversample underrepresented groups or undersample overrepresented groups. Reweighting assigns different importance to training examples, giving higher weight to underrepresented groups. These techniques ensure balanced training but may reduce dataset size or introduce sampling artifacts. In-processing techniques constrain model training to satisfy fairness objectives. Add fairness constraints to the loss function. Penalize violations of demographic parity or equalized odds. Train adversarial debiasing models that remove information correlated with sensitive attributes while preserving predictive power. These techniques integrate fairness directly into learning but may reduce overall accuracy. Post-processing techniques adjust predictions after training to satisfy fairness metrics. Calibrate thresholds separately for different groups. Adjust scores to achieve demographic parity or equalized odds. These techniques are flexible and preserve model training, but may feel like fixing rather than addressing root causes. Careful feature engineering removes protected attributes, race, gender from features. But beware proxies. Zip codes correlate with race, names with gender. Removing obvious protected attributes isn't sufficient if proxies remain. Testing for proxy variables requires careful analysis. Continuous monitoring tracks fairness metrics after deployment. Models degrade over time as data distributions shift. Regular auditing catches fairness violations before they cause widespread harm. Monitoring is essential for responsible deployment. Federated learning enables training models on sensitive data without violating privacy. Traditional ML centralizes data, collect everyone's data, aggregate it in one place, train a model. This creates privacy risks. Central data storage is a target for breaches. Users must trust the centralized party. Regulations like GDPR restrict data centralization. Federated learning keeps data distributed. Imagine training a predictive keyboard model. Millions of phones have typing data, but users don't want to share it. Federated learning works as follows. The server sends the current global model to participating clients, phones. Each client trains locally on its private data, computing gradients. Clients send gradients, not data, back to the server. The server aggregates gradients and updates the global model. Repeat for many rounds. The key insight: gradients carry less sensitive information than raw data. Users never share their actual messages. The server never sees individual data. Privacy is substantially improved, though not perfect. Gradients can still leak some information about training data. Federated learning faces challenges. Communication costs. Sending model updates repeatedly is expensive. Non-IID data, different clients have different data distributions, complicating training. Stragglers, slow clients delay training. Adversarial clients, malicious participants could send corrupted updates. Applications include mobile keyboards. Google's Gboard uses federated learning. Healthcare, training on patient data across hospitals without sharing records. Finance, fraud detection across banks. And IoT devices. Federated learning enables ML on decentralized, privacy-sensitive data. Differential privacy provides mathematically rigorous privacy guarantees. The core idea: add carefully calibrated noise to outputs so that including or excluding any individual's data causes minimal change in results. If an adversary can't determine whether you participated in a dataset based on query results, your privacy is protected. Formally, a mechanism is E-differential private if for any two datasets differing in one individual's data, the probability of any output changes by at most a factor of EI. Small e means strong privacy. Outputs barely change when individuals are added or removed. Large E means weak privacy but more accurate results. How does it work? When someone queries a dataset, what's the average income? Add noise calibrated to the query's sensitivity. How much one person could change the answer. The noise masks individual contributions while preserving aggregate statistics. Multiple queries consume privacy budget. More queries require more noise or tighter privacy bounds. The trade-off is fundamental: privacy versus utility. Strong privacy, small a, requires significant noise, degrading utility. Weak privacy, large e, requires less noise, preserving utility but offering less protection. There's no free lunch. Organizations must balance stakeholder needs. Applications include census data release. US Census uses differential privacy. Medical research, analyze patient data without identifying individuals. Corporate analytics, companies analyze user behavior while protecting privacy. And federated learning, add differential privacy to gradient updates for additional protection. Differential privacy is the gold standard for formal privacy, but requires careful calibration and understanding of privacy-utility trade-offs. Black box models make predictions without explaining why. Explainability techniques address this. Interpretability and explainability differ subtly. Interpretability is understanding the model's overall logic, how it works internally. Linear models are interpretable. Coefficients show feature importance. Explainability is understanding specific predictions. Why this particular input received this output. You might not understand the full model, but can explain individual decisions. SHAP, Shapley Additive Explanations, uses game theory to compute feature importance. For each prediction, SHAP assigns each feature a value representing its contribution. Positive values increase the prediction, negative values decrease it. SHAP satisfies desirable properties: consistency, local accuracy, and missingness. It works for any model but is computationally expensive. LIME, Local Interpretable Model Agnostic Explanations, approximates complex models locally with simple, interpretable models. For a specific prediction, LIME perturbs the input, observes output changes, and fits a linear model approximating the complex model's behavior in that local region. The linear model is interpretable, explaining that particular prediction. LIME is fast and model agnostic, but only locally accurate. Attention visualization for transformers shows which input tokens the model attends to when making predictions. High attention weights indicate important tokens. This helps understand what information the model uses. Attention isn't perfect explainability. Attention doesn't always correspond to causation, but provides useful insights. Explainability builds trust, enables debugging, and satisfies regulatory requirements. In high-stakes domains like healthcare and finance, explainability is increasingly required. AI safety addresses ensuring systems behave as intended, especially as capabilities increase. The specification problem, translating human goals into mathematical objectives, is hard. You want a robot to clean your house. You specify maximize cleanliness. The robot pours cleaning solution everywhere, technically achieving the objective but causing havoc. The specified objective didn't capture your true goal. This isn't a toy problem. Real systems exhibit specification gaming. Reward hacking occurs when systems exploit loopholes in reward specifications. An RL agent playing a boat racing game discovers that circling to collect power-ups repeatedly scores more points than actually racing. It technically maximizes reward but violates the spirit of the task. Reward hacking is common. Specifications rarely perfectly capture intentions. Goal misalignment is broader. AI systems optimize for proxies that correlate with but don't match true objectives. Recommendation systems optimizing for engagement may promote divisive or addictive content. Content moderation systems minimizing reported violations may suppress unpopular but harmless speech. The measurable proxy diverges from the true goal. Robustness means systems handle distribution shifts, adversarial inputs, and edge cases reliably. Models trained in controlled settings fail when deployed in noisy, adversarial, real-world conditions. Adversarial examples, carefully crafted inputs causing misclassifications, demonstrate brittleness. Robust AI performs reliably despite environmental variations. Value alignment ensures AI systems share human values and act in humanity's interest. As AI capabilities grow, misaligned superintelligent systems pose existential risks. Research on value alignment addresses specifying human values, learning values from human feedback, and ensuring AI systems robustly pursue these values. Deploying AI responsibly requires more than accurate models. It requires operational rigor. Model monitoring tracks performance after deployment. Accuracy, fairness, latency, and data distributions shift over time. Concept drift means the relationship between inputs and outputs changes. Data drift means input distributions change. Without monitoring, degradation goes unnoticed until causing harm. Continuous monitoring enables early detection and remediation. A/B testing enables cautious rollout. Deploy the new model to a small fraction of traffic while most users see the baseline. Compare outcomes. Does the new model improve metrics? Does it introduce fairness violations? Does it cause unexpected behaviors? Gradual rollout reduces risk from unforeseen failures. Human in the loop keeps humans involved in critical decisions. AI assists but doesn't replace human judgment in high-stakes contexts. Medical diagnosis, AI flags potential issues, but doctors make final calls. Loan decisions involve human review. Fully automated critical decisions without oversight create risks. Graceful degradation provides safe fallbacks when models fail or confidence is low. If confidence is below a threshold, escalate to human review or use conservative defaults. Systems shouldn't fail catastrophically when models make mistakes. Safe failure modes are part of responsible design. Transparency documents model capabilities, limitations, and intended use cases. Model cards describe training data, performance metrics, known biases, and appropriate applications. Users and stakeholders understand what the model can and cannot do. Transparency enables informed decisions about deployment and use. Adversarial examples reveal brittleness in neural networks and pose security risks. An adversarial example is an input with small perturbations designed to cause misclassification. Add carefully crafted noise to an image of a panda. Humans see a panda, but the model confidently classifies it as a gibbon. The perturbations are imperceptible to humans but completely fool models. This isn't limited to images. Adversarial examples exist for text, audio, and other modalities. Why do adversarial examples exist? Neural networks learn boundaries between classes. These boundaries can be surprisingly close to training points in high-dimensional spaces. Small steps in certain directions cross boundaries, causing misclassifications. Models are locally linear, so gradient-based perturbations can systematically exploit this. Adversarial training hardens models by including adversarial examples during training. Generate adversarial perturbations and train the model to classify them correctly. This improves robustness, but is computationally expensive and doesn't provide guarantees against stronger attacks. It's an arms race. Attackers develop stronger attacks, defenders develop stronger defenses. Certified defenses provide provable robustness guarantees. Prove that no perturbation within a certain radius can change the prediction. These defenses use techniques from formal verification and are computationally expensive but offer strong guarantees. They're advancing but not yet practical for large models. Adversarial examples pose serious risks in security-critical systems. Autonomous vehicles fooled by adversarial stop signs could cause accidents. Spam filters defeated by adversarial text fail to protect users. Face recognition systems spoofed by adversarial images undermine security. Robustness research addresses these risks. Ethical frameworks guide AI development decisions and prioritization. Utilitarianism focuses on consequences, maximize overall benefit, and minimize harm. Utilitarian AI development weighs costs and benefits, aiming for net positive outcomes. Challenges include measuring harms and benefits, handling trade offs between groups, and addressing uncertainty about consequences. Utilitarian reasoning risks sacrificing minority interests for majority benefit. Deontology focuses on duties and rights. Certain actions are right or wrong regardless of consequences. Respecting privacy, avoiding deception, and ensuring informed consent are duties. Deontological AI development respects individual rights even when violating them might increase aggregate welfare. Challenges include conflicts between duties and inflexibility in complex situations. Virtue ethics focuses on character, cultivate virtuous traits in developers and organizations. Honesty, responsibility, humility, and compassion guide behavior. Virtue ethics emphasizes culture and values, not just rules. Challenges include defining virtues and resolving conflicts between virtuous dispositions. Justice and fairness emphasize equitable treatment. Distributive justice addresses fair allocation of benefits and burdens. Procedural justice ensures fair processes. Corrective justice addresses harms and restitution. Fairness requires considering historical injustice and power imbalances. Challenges include conflicting fairness definitions and addressing systemic inequalities. Stakeholder engagement involves affected communities in design and deployment decisions. Those impacted by AI systems should have input into their development. Participatory design incorporates diverse perspectives and addresses community concerns. Challenges include who represents communities and balancing conflicting interests. Governance structures shape how AI is developed and deployed responsibly. GDPR, General Data Protection Regulation in Europe, establishes data protection rights, consent for data collection, right to access and deletion, data portability, and automated decision-making transparency. GDPR impacts AI significantly. Models trained on EU data must respect these rights. Right to explanation implies some model interpretability. GDPR demonstrates regulatory approaches balancing innovation and protection. Algorithmic accountability regulations require transparency and auditing. Proposed laws mandate disclosure of AI use in consequential decisions. Algorithmic impact assessments evaluate risks before deployment. Independent audits verify compliance with fairness and accuracy standards. Accountability regulations make developers responsible for outcomes, incentivizing responsible practices. Sector-specific regulations apply AI differently in different domains. Healthcare AI faces FDA approval and hypercompliance. Financial AI must comply with fair lending laws and anti-discrimination regulations. Autonomous vehicles face transportation safety standards. These regulations reflect domain-specific risks and existing regulatory frameworks. Industry self-regulation includes ethical guidelines and best practices. Companies adopt principles like fairness, transparency, and privacy. Industry consortia develop standards. Self-regulation is flexible and fast but lacks enforcement. Effective self-regulation requires commitment beyond lip service and external accountability. International cooperation aligns standards across jurisdictions. AI doesn't respect borders. Models trained globally, deployed everywhere. Divergent regulations fragment markets and complicate compliance. International agreements on ethical principles and standards enable responsible innovation while protecting rights. Cooperation is challenging but necessary. AI's impacts extend beyond individual applications to shape society. Job displacement concerns arise as AI automates tasks. Transportation, autonomous vehicles, customer service, chatbots, manufacturing, robotics, and even creative work, AI writing and art, face automation. While new jobs emerge, transitions are disruptive. Policies addressing retraining, safety nets, and income support are crucial. The distribution of automation's benefits matters. Who gains, who loses? The digital divide means unequal access to AI's benefits. Advanced AI requires data, compute, and expertise concentrated in wealthy nations and organizations. Developing regions lack resources to build and deploy AI. Even within countries, rural areas and disadvantaged communities have less access. Bridging this divide requires investment in education, infrastructure, and capacity building. Power concentration happens as AI capabilities concentrate in a few large organizations. Training state of the art models costs millions, accessible only to tech giants. These organizations control valuable AI systems, shaping information flow, economic opportunities, and social interactions. Concentration raises concerns about monopoly power, democratic accountability, and value alignment. Open source models and research democratize access but can't fully address resource disparities. Misinformation risks grow with AI generated content. Deepfakes create realistic fake videos. Language models generate convincing but false text. Automated bots spread disinformation at scale. Distinguishing real from synthetic content becomes harder. Misinformation undermines trust, polarizes society, and manipulates public opinion. Detection and authentication technologies are critical. Environmental impact includes massive energy consumption. Training large language models emits substantial CO2. Inference at scale consumes enormous electricity. As models grow, environmental costs increase. Green AI research develops efficient algorithms and hardware. Balancing AI's benefits against environmental costs is an emerging concern. Tomorrow is day 9, generative AI and large language models. We dive deep into models that generate novel content. We'll trace the evolution of generative models. GANs, Generative Adversarial Networks, introduced adversarial training for realistic generation. VAEs, Variational Autoencoders, use probabilistic latent spaces. Diffusion models gradually denoise random noise to generate high-quality samples. Each approach has strengths and applications. We'll explore large language models in depth. GPT-2, GPT-3, GPT-4. How did scaling change capabilities? What are scaling laws predicting model performance from size and data? What emergent abilities appear at large scale that weren't present in smaller models? We'll understand the architecture, training, and impressive capabilities of modern LLMs. We'll master prompt engineering, crafting inputs to guide model outputs effectively. Few-shot learning, chain of thought prompting, and instruction following enable flexible task performance without fine-tuning. Prompting is becoming a key skill for leveraging LLMs. We'll examine multimodal models combining vision and language. CLIP connects images and text. DAL-E and Stable Diffusion generate images from text prompts. GPT-4 accepts both text and images. Multimodal AI enables richer interactions and novel applications. Finally, we'll assess capabilities and limitations. What can generative AI do well? What are persistent challenges, hallucinations, reasoning failures, bias? Understanding both strengths and weaknesses is crucial for responsible use. Excellent work today. You now understand AI ethics, privacy, fairness, and safety? Tomorrow we explore the cutting edge of generative AI. See you then.